Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 16, Designing Your Factory Before You Build It. Most design mistakes become obvious only after production starts, when it's too late and too expensive to fix. In this episode, we explore how virtual simulations and 3D factory models can prevent layout issues, bottlenecks, and costly redesigns before construction even begins. You'll hear how DBR77 enables companies to test different layouts, simulate material flows, and plan smarter using operational data, all before pouring the first foundation. We show how better design decisions lead to faster startups, lower costs, and smoother operations from day one. Factory on Air is powered by DBR77, the platform that lets you simulate, optimize, and future-proof your factory before it exists. Let's get started.
There's this universal pain, I think, shared by pretty much every executive, every engineer, anyone involved in these massive industrial projects. You spend years, maybe billions, building some huge new facility, a gigafactory maybe, or a complex logistics hub, a giant assembly plant, and then you finish construction, you flip the switch, the first shift clocks in, and almost immediately you realize the design has major flaws. We're talking about starting production, finally getting things moving, only to discover these massive systemic problems that are literally baked into the concrete foundation. Maybe the lines are completely unbalanced. You've got a super expensive automated station just sitting idle for like 20 minutes while the one right before it is totally jammed up. Or maybe the storage area is just way too cramped. You can't stage materials properly, and suddenly you've got constant logistics bottlenecks inside the building. It seems like we learn about these really fundamental design mistakes after the first shovel has already hit the dirt, doesn't it? And that leads to budget overruns that aren't just numbers on a spreadsheet. They can force serious organizational changes.
Exactly. And the cost of waiting for those physical mistakes to actually show up is not just astronomical financially. It's a real competitive liability. You can lose months, sometimes even years, trying to fix these fundamental errors while your competitors are already scaling up their operations. So this deep dive today is really about the power of planning ahead, doing things preemptively. It's about how we can leverage digital simulations, these immersive virtual environments, and specifically thinking about solutions like those offered by DBR77 to design and basically test the perfect factory before a single brick is laid. We're really exploring how this comprehensive data-driven approach completely flips that old reactive script. Instead of dealing with costly infrastructure changes later on where, every single change order probably has a six-figure price tag and delays production even further, we're correcting parameters, moving virtual assets around inside a digital model. We're essentially stress testing reality, but we're doing it digitally, where the cost of change is almost zero.
Okay, so our mission today, for everyone listening, is to kind of give you the shortcut to really understanding this. Especially if you're managing or investing in these huge capital projects, this is the essential stuff you need to know. We're focusing on preventing those incredibly expensive, time-consuming errors in projects where, let's face it, the stakes couldn't be higher. We need to really get specific about what failures we're trying to defend against. Right, let's unpack this in more detail. We get the general idea of chaos, but what are the specific sort of chronic consequences that happen when you start a factory based just on, say, 2D blueprints and maybe some generalized assumptions? What are the actual disasters we're aiming to avoid by using deep simulation?
Well, the problem usually isn't just one single catastrophic failure. It's more often a combination, a confluence of these chronic issues that just slowly drain profitability over the long haul. I'd say the first, and probably the most damaging consequence, is inefficient operations. And that usually stems directly from those unbalanced production lines you mentioned. If your simulation wasn't run rigorously enough, or maybe worst case it wasn't run at all, you almost inevitably end up with these massive gaps in throughput between different stages. What happens is this creates chronic downtimes. And of course, massive yield losses because the entire facility can only move as fast as its slowest, most congested bottleneck.
Yeah.
We often see situations where maybe there's a highly complex, really expensive piece of machinery. Maybe it's capable of cycling every 10 seconds, but it ends up sitting idle for maybe 40% of the day. Why? Because the manual assembly station just upstream can only feed it parts once every 30 seconds. That massive loss in utilization, well, that's just pure unnecessary financial waste right there.
Okay. So the issue isn't simply that the whole system is slow overall. It's that specific machines, often the ones representing the biggest capital investment, are just sitting there waiting for parts. And that's down to poor flow sequencing, or maybe buffers aren't sized right, or maybe it's just a fundamentally bad layout.
Precisely. And this inefficiency often ties directly into the next major blunder: issues with space and logistics. In facilities that haven't been planned well, you frequently find that the warehousing areas or maybe the internal logistical zones are just drastically undersized. Or sometimes, even if they technically have enough square footage, they're just poorly situated relative to the production lines they're supposed to be serving. And this causes constant, really systemic material flow conflicts. Think of it like having permanent rush hour traffic, but inside your building. You've got forklifts queuing up just to unload materials. Staging areas are overflowing into walkways. Critical material deliveries maybe have to cross right through high-traffic production zones. This doesn't just slow things down, it introduces serious safety hazards. It makes material availability unpredictable. And it turns what should be a smooth, synchronized operation into this kind of unpredictable mess that needs way too much human oversight just to manage the day-to-day chaos.
That makes total sense, yeah. If your internal transport vehicles, your forklifts or AGVs or whatever, are constantly navigating choke points, or maybe they have to travel 3 times the optimal distance just to get material from the receiving dock to the actual production line, well, you fundamentally failed in the layout planning stage, haven't you? And I imagine that wasted distance immediately translates into wasted human effort, too.
It absolutely does. And that's often the silent profit killer that people don't even measure properly. We've actually documented cases where employees lose cumulative hours every single week just due to unnecessary travel or excessive movement across the shop floor. In a factory that was designed without proper simulation, even simple tasks can require excessive walking. Maybe searching for tools or parts because storage isn't localized near the point of use, or just waiting in line behind some internal transport conflict. These seconds and minutes, they really accumulate throughout a shift. And over a year, that becomes thousands upon thousands of hours of lost labor efficiency, pure waste. And we absolutely have to talk about the non-negotiable issues too. Safety and human factors, ergonomics. Beyond just efficiency, a poor design can severely impact things like machine access for maintenance, or even basic security protocols. Think about it. If your maintenance teams can't easily access key components on a machine without having to shut down adjacent machinery, or maybe contort themselves into cramped, awkward positions, well, then maintenance takes longer. It's inherently more dangerous, and your overall equipment effectiveness plummets.
And the human ergonomics side of things, I imagine those failures are often only discovered much later, maybe when injury rates start to spike or perhaps employee turnover increases in certain areas.
That's very often the case, unfortunately. It's usually only after the plant is up and running that managers might realize, oh, this particular assembly point, or maybe this machine interface. It actually requires workers to strain or twist or bend repeatedly all shift long. And if that wasn't caught and corrected in a virtual environment beforehand, the consequences are pretty severe. High injury rates, musculoskeletal disorders, which lead to high employee turnover, absenteeism, and eventually really expensive compensatory costs. So when you combine all these chronic issues, the idle machinery, the logistical gridlock inside the plant, all that wasted human effort, plus the safety hazards, the unavoidable end result is that massive financial hit we talked about earlier. The absolute necessity of immediate, really expensive infrastructure modifications. You've just celebrated the grand opening of the plant, maybe cut the ribbon, and now you find you have to immediately reinvest millions just to make the facility minimally functional, let alone optimal. That's precisely the cycle of reactive, poor design that solutions like those from DBR77 are specifically engineered to break.
What's truly fascinating here, I think, is how simulation fundamentally shifts error identification. It moves it from the high-cost, high-risk physical world where, fixing a badly placed wall could cost hundreds of thousands into the infinitely cheaper and safer virtual world. It really is the core defensive strategy against all these pervasive design flaws we've been discussing.
Yeah, I understand that contrast. Instead of finding out 6 months into production that your main conveyor belt is sized incorrectly, you find out while it's still just lines in a digital model, maybe before the building's even a concept drawing. But maybe for our listeners who are a bit more technically inclined, how exactly do these sophisticated simulations work? Can you elaborate a bit on the underlying principles? What allows them to accurately predict these potential future operational failures?
That's an excellent question. And you're right, it's not magic. It's really applied mathematics and computer science working together. The primary mechanism is what we call comprehensive testing of the factory layout before any physical building starts. The simulation platform, essentially the digital twin, isn't just built geometrically like a 3D picture, it's built mathematically as well. We use advanced modeling techniques like discrete event simulation, or DES. This approach models the facility as a sequence of distinct, separate events. A part arriving at a station, a machine starting its processing cycle, an operator moving from point A to point B. And crucially, by introducing statistical variability into the model, things like the chance a machine might break down or maybe a delivery truck is late, we can accurately model the real-world complexity and, importantly, the randomness that simple spreadsheet models just cannot capture.
Okay, so it's not just running basic averages then. You're actually applying concepts like queuing theory to predict where backups might occur and using stochastic modeling to account for all that inherent variability and uncertainty you find in real-world manufacturing.
Exactly right. You absolutely have to account for the variability. Otherwise, the model isn't realistic. These modeling capabilities allow us to simulate and analyze the flow of materials, the movement of people, and critically, the performance of machinery under all sorts of stress scenarios. That could include predictable things like scheduled maintenance or shift changes, but also unpredictable events like machine failures or sudden spikes in customer demand. We determine the optimal placement for everything, storage areas, assembly lines, service points, by running potentially thousands of iterations of these different scenarios. So the output isn't just a vague suggestion, it's usually a statistically validated optimization, telling you the best configuration based on the data.
That sounds incredibly robust. But it strikes me that this entire process relies heavily on feeding the model extremely accurate information to begin with. You know the old saying, garbage in, garbage out.
Yeah.
For many established companies, especially those maybe with older legacy systems, gathering the necessary precise data, things like accurate cycle times, machine reliability stats, even operator walking speeds, that must be a huge barrier to entry, right? How do companies actually overcome that potential paralysis caused by messy or incomplete data?
You've hit on probably the biggest challenge, honestly. The quality of the input data is absolutely paramount, and we really do treat data as the foundational bedrock of the entire project. The inputs required are incredibly precise. Validated cycle times for every single operation, anticipated batch sizes for different products, specific logistical needs like truck turnaround times, and of course, all the relevant occupational health and safety requirements, BHP, ergonomics, etc. If you feed the model guesswork or outdated assumptions, then the output, no matter how sophisticated the simulation, will just be an optimized fantasy. It won't reflect reality. This is precisely why any comprehensive platform in the space must start with rigorous data validation. Now, if a client genuinely doesn't have reliable internal data for certain processes, maybe it's a completely new product line, then we have to utilize historical references and benchmark data. By using validated performance data from other similar facilities, or perhaps benchmark simulations based on established industry best practices, we can create reliable proxy models to fill those gaps. This allows us to still accurately predict the spatial needs and design a truly tailored facility. The goal is always optimization, avoiding both excessive, costly spare room and also avoiding crippling constraints that limit future growth. And that optimization has to be built on the strongest available data foundation we can get.
Okay, here's where it gets really interesting for me. How do specific solutions, like the DBR77 platform you mentioned, actually put all this theory, this complex data analysis and mathematical simulation into practice? It sounds like we're moving way beyond just static 2D CAD drawings here into something that's fully interactive and predictive.
That's exactly the critical distinction. Yes, DBR77's core offering, particularly in this facility planning space, is the creation of a highly sophisticated 3D digital twin. And crucially, like you said, this isn't just a pretty visual model you can spin around on screen. It's a living virtual representation, yes, but it's also a mathematical replication that accurately mirrors the planned line layout, all the storage areas, the supporting infrastructure, often down to the square centimeter.
Yeah.
In essence, it is the facility just existing as pure data before it exists in concrete and steel.
So what specifically can someone, say an engineer or maybe a facilities manager, actually do inside this digital twin environment that they just couldn't do with a static blueprint or even a simple 3D model? Can they, for instance, simulate what happens if a key machine breaks down right in the middle of a peak production shift?
Absolutely, yes. It functions as a truly dynamic user testing environment. You can absolutely introduce chaos, just like in the real world. Users can test various layout configurations almost in real time. For example, you could virtually move an entire assembly cell 20 meters further down the line and immediately see the ripple effect it has on material flow paths, on operator travel times, on WIP inventory levels. You can simulate the failure of a critical machine, just as you asked, and then watch how the buffer zones, both upstream and downstream, react. Do they overflow? Do they starve the next process? Furthermore, users can analyze operational and material flows under various stress conditions, not just normal operation. And they can verify vital infrastructure access points. This is incredibly important for regulatory compliance and safety, ensuring maintenance technicians can actually reach every required panel for scheduled maintenance without needing specialized lifts or causing excessive downtime, or ensuring that designated fire safety pathways are never ever blocked by staged material, even during peak production scenarios.
This kind of active testing capability saves enormous amounts of time, money, and potential liability during the actual commissioning phase later on. And underpinning all of this is dynamic data integration. The simulations don't just use static data, they incorporate real operational data if it's available from similar existing processes. And, very importantly, they integrate future production forecasts. This means you're not just modeling the factory to handle today's capacity requirements, you're actively stress testing it for the capacity you project you'll need in, say, 5 years' time. This ensures the facility is designed to be scalable right from day one, avoiding costly retrofits later.
Okay, let's try and ground this in reality a bit. Can you share some tangible success stories? What are the kind of aha moments that really prove the return on investment for this level of intense pre-planning? Because, let's be honest, spending all this time and effort building and testing a virtual environment is an investment in itself, isn't it?
It absolutely is an investment, yes. But the key is that the returns are often immediate, significant, and highly quantifiable. We have several really compelling examples. Consider the case of a large electronics factory. They used DBR77's virtual design tools to meticulously optimize the placement of every single workstation. They rationalized the flow paths for thousands of different components, and they strategically placed centralized material delivery points to minimize travel. The final validated outcome: a documented 35% reduction in component flow time across the facility.
35%, wow, that is a massive efficiency gain, especially in high-volume electronics where cycle times are often measured in milliseconds. That's a genuine competitive game changer, right? It immediately impacts the cost per unit produced.
It absolutely is. A huge impact. Here's another great example, this time involving a packaging manufacturer. Their initial facility plans, based on traditional methods, included constructing an entirely new, quite sizable warehouse building just to handle their projected inventory levels and unloading operations. However, through rigorous simulation of their inbound logistics, modeling the truck arrivals, the unloading procedures, optimizing storage density using the digital twin, the model actually revealed something crucial. It showed that their existing space, if it was optimized correctly for flow and density, was entirely adequate. They didn't need new building. So by optimizing the virtual flow and the storage density within the existing footprint, they completely avoided the need to construct that additional warehouse. This resulted in a documented saving of 1.2 million Polish zloty just by avoiding the unnecessary construction costs. And that's not even counting the perpetual operational savings from not having to heat, cool, light, or staff a building they ultimately didn't need.
Avoiding construction altogether. Yeah, that's probably the ultimate saving, isn't it? That really demonstrates the core principle here. Sometimes smarter design actually means smaller or more contained design, not just bigger.
Precisely. Well said. And one final quick example. We worked with an automotive company that was facing extreme pressure to maximize their production output, but they were constrained within a fixed industrial plot. They couldn't expand outwards. But by utilizing detailed 3D simulation during their design phase, they were actually able to decrease the required overall production area by a full 20%. And they did this while maintaining, and in some areas even slightly increasing, their full operational efficiency targets. This optimization saved them significantly on real estate costs, ongoing heating and utility costs, and initial construction costs. It really shows how virtual optimization translates directly into tangible physical space and financial savings. Now, if we connect this back to the bigger picture, it's important to understand that DBR77 isn't just offering a highly specialized tool for facility design. It's really presenting an integrated ecosystem, one that's designed for achieving total digital transformation across the entire industrial enterprise. You could say the optimized facility design is often just the starting point for a much broader, more strategic overhaul of how the company operates.
Okay, that transition makes sense. Once a company has gone through the effort of creating an accurate, validated digital twin of its physical plant, that detailed data model itself becomes incredibly valuable for all sorts of other strategic operations, right? So what's the overarching mission here? How does a platform like this move beyond just optimizing the layout and start impacting the entire enterprise structure?
The core vision, really, is to enable industrial companies, whether they're involved in discrete manufacturing, process industries, or complex logistics, to achieve significantly higher levels of efficiency, radical transparency across their operations, and ultimately accelerated innovation.
The platform aims to fundamentally transform those traditional, often siloed industrial processes. And it does this by integrating several foundational technologies: the Internet of Things, IoT for data capture, the digital twins for modeling and simulation, artificial intelligence, AI for analysis and prediction, and even a smart marketplace to connect companies with automation solutions. It's really about creating these intelligent, potentially self-optimizing industrial ecosystems.
Right. So the digital twin for the facility design acts as the visualization and testing hub, but as we discussed, it needs that constant stream of high-quality information to function optimally over time. Which brings us back to the importance of data collection, I suppose.
Absolutely. It really has to start there. So within the ecosystem, you have integrated solutions specifically for real-time data collection. That's the essential IoT layer. This typically involves implementing systems, often using dedicated sensors, to monitor key machine parameters, maybe energy consumption, process variables, quality outcomes, all in real time. And the goal here isn't just about gathering vast quantities of raw numbers. It's about ensuring the accuracy and timeliness of that data. It's about reducing the massive amounts of manual time that people previously spent just gathering information. And it's about enabling better, faster, data-driven operational management decisions, sometimes even in real time.
Okay, data collection seems like the logical entry point, but the whole journey towards full digital transformation often seems incredibly bewildering for companies, doesn't it? There are dozens of different technologies out there, countless buzzwords, massive investment decisions to make. How does a company even know where to start or what to prioritize in that complex landscape?
That's a very common challenge. And it's precisely where another component, the Digital Development Roadmap, or DRD, becomes vital. Think of the DRD as a comprehensive strategic tool. It's specifically designed to tackle that uncertainty and help companies avoid analysis paralysis. It provides a structured, standardized framework to objectively assess a firm's current digital maturity level. It asks the hard questions. Where are they really on the curve today in terms of their IT infrastructure, their data governance practices, the digital skill set of their employees? Then, the DRD process analyzes the relevant technological megatrends. What are the industry leaders doing? What technologies are proving effective for their specific challenges? And based on that assessment and analysis, it helps the company create a detailed, prioritized development and implementation plan. It structures this roadmap across more than 27 different operational, development, and technological areas, giving managers real clarity. It helps them set achievable strategic initiatives that directly link digital transformation efforts to core business goals, like reducing scrap rates, improving on-time delivery, or accelerating new product introductions.
That sounds incredibly powerful, especially for the C-suite, providing a clear, measurable path forward instead of just vague ambitions. But okay, let's say they have that strategy defined by the DRD, and they realize, based on the plan, that they need to automate 3 new production lines to meet their goals. How does the platform then help them actually execute that automation? Because finding the right suppliers, the right system integrators, especially on a global scale, can be a massive time-consuming challenge in itself.
Yes, and that specific challenge is addressed by the intelligent marketplace component of the ecosystem. This platform essentially acts as a sophisticated digital intermediary. It connects industrial companies directly and transparently with a network of pre-vetted automation suppliers and certified system integrators. This is actually a crucial element for dramatically accelerating the implementation phase of any automation project. Just consider the traditional route for a moment. The average automation process length, starting from the initial planning, drafting detailed specifications, going through solution selection, finding a capable integrator, negotiating contracts, then the actual implementation, and finally optimization. That entire process can easily consume 25 months. That's over 2 years just waiting to start seeing the return on investment.
2 years. Wow. In today's competitive landscape, that feels like an eternity, doesn't it? Things change so fast. So how does this intelligent marketplace manage to potentially cut that time in half? What's the mechanism?
It primarily leverages AI and process standardization. The platform allows a company to upload its detailed project specifications, which, by the way, are often generated directly from the digital twin simulations or the DRD strategic plan. The AI algorithms then automatically match those requirements against a curated, constantly updated database of certified supplier capabilities and integrator expertise. It filters and presents the best fit, most relevant solutions almost instantly. This transparent and automated comparison dramatically speeds up the tendering process, often shaving several weeks off just that initial selection phase. It eliminates a huge amount of back and forth emails and meetings, allowing everyone to focus on the technical solution and execution rather than getting bogged down in procurement paperwork. And the data we've seen suggests that this streamlined process doesn't just shorten the overall implementation time significantly, potentially by half, as you said. It also drives considerable cost efficiency. We typically see savings of around 30% specifically at the purchase and implementation stage. This comes from more transparent pricing, better optimized solution selection, and reduced negotiation overhead. It effectively transforms what used to be a lengthy, often opaque procurement process into a much faster, data-driven transaction.
Okay, that level of digital integration, connecting strategy to execution via a marketplace, that implies pretty massive shifts in how companies manage capital expenditure and operational budgets. I imagine this can be quite intimidating for chief financial officers, the CFOs, who really need ironclad ROI projections before they sign off on such comprehensive, potentially costly changes. What specific support is built into this ecosystem for the finance and procurement teams who hold the purse strings?
That's a critical point, and yes, there is dedicated financial and procurement support integrated throughout the platform. It absolutely recognizes that technology adoption has to be fiscally sound and strategically justified. For the CFOs, there are sophisticated, often AI-driven tools available. These tools help analyze the projected return on investment, ROI, with much greater accuracy than traditional methods. They assist in planning budgets more effectively and assessing the total cost of implementation, including often overlooked integration costs, with a high degree of predictive accuracy. This significantly helps manage the inherent financial risk associated with large-scale automation projects. It can also assist companies in securing financing because they can present potential lenders or investors with a solid, data-backed proof of profitability based on a validated, digitally planned roadmap. It essentially takes a lot of the guesswork out of capital planning for major transformations.
And what about the procurement teams? They're the ones ultimately responsible for vendor selection, negotiating contracts, and ensuring cost control throughout the process.
For procurement professionals, the platform provides highly automated support tools as well. These include features for real-time comparison of offers, based on predefined technical specifications and budgetary constraints set by the company. There are objective supplier evaluation tools, helping to score vendors based on capabilities, certifications, past performance, and other criteria, and mechanisms to ensure cost transparency throughout the bidding and selection process. This ensures that when new technology or integration services are selected, the decision is based on the most informed, most cost-effective choice possible. It also helps minimize the risks of vendor lock-in or unexpected cost overruns later in the project. The entire DBR77 ecosystem, really, is designed to minimize risk across the board: technical risk, financial risk, implementation risk, and maximize the strategic, measurable advantage for the company.
That paints a really compelling picture of a robust, fully integrated system connecting all the dots. Now let's bring it back down to the practical level, back to the physical plant design we started with. If a company is convinced they see the power of this preemptive simulation approach, and they're ready to actually start this virtual design process for a new facility or maybe a major line refurbishment, what does that journey look like? What are the actionable steps they need to take, starting from, say, a blank page, to get to that fully optimized digital twin?
Right, okay. There are essentially 6 practical sequential steps that generally underpin a successful facility design process using this kind of simulation technology.
Yeah.
The very first step, and as we discussed, probably the most critical one, is gathering absolutely crucial verified data. This covers everything about the plant production: the specific parameters, detailed machinery specifications, all logistical requirements, inbound, outbound, internal, and anticipated human workflows, including ergonomic factors. If you try to shortcut this step or use poor quality data, your digital twin might look impressive, but it'll essentially be a fun video game, not a useful planning tool. Data is king here.
Data collection and validation first.
Got it.
What's the next critical phase once that solid data foundation is in place?
Step 2 is actually creating the digital model itself, building the geometric and mathematical digital twin of the facility. This is where the physical layout is constructed virtually, piece by piece, incorporating all those precise data inputs we just gathered into the simulation engine. This stage essentially defines the rules, the physics, the process logic, the constraints by which this virtual world will operate.
Okay, so you build the virtual sandbox. Then I assume you put that model through its paces, really test it out.
Exactly. Step 3 involves rigorous and iterative testing of various layout configurations. This is crucial. It means actively testing different placements for machinery, experimenting with different buffer sizes or queuing strategies for personnel and materials, trying out different storage methodologies or picking strategies. And you don't just test the one ideal scenario that looks good on paper. You deliberately test dozens, maybe hundreds, of variants to find the arrangement that is not only efficient, but also the most robust, the one that performs well under a range of conditions. Following that intensive testing, step 4 involves deep analysis of the results. We analyze the material flows under both optimal conditions and also under various stress conditions like machine breakdowns or demand surges. And critically, we attest scenarios specifically related to future production growth and scaling. A design might work perfectly fine for today's volume, but we need to know how that layout holds up when demand potentially doubles next year, or if a completely new product line needs to be integrated into the same space. This predictive scalability analysis is where the long-term ROI truly multiplies.
And before you finalize everything, you absolutely have to circle back to the safety and human factors again, right? Ensure the design isn't just efficient on paper, but actually compliant, safe, and sustainable for the workforce who will operate it.
Precisely. That's step 5, verification. This involved explicitly verifying all the safety protocols within the simulated environment, checking ergonomic factors for key tasks, confirming service accessibility for maintenance. You ask questions like, can maintenance crews safely access this specific machine component with the required tools and equipment without undue risk? Does this proposed workstation design maintain optimal ergonomic conditions for, say, 95% of the expected operator population? These are absolutely non-negotiable checks that the simulation must pass before sign-off. And then finally, step 6 is adjusting and formalizing the final physical design based on all those robust simulation results. This ensures the actual blueprints given to the construction team are a perfect, optimized reflection of the validated virtual model.
That detailed 6-step process sounds incredibly thorough, almost ideal. But I noticed the source material we looked at is careful to point out that this whole process isn't necessarily easy. It's not without its hurdles. So for a manager out there who's considering implementing this kind of approach, what are the key difficulties they really need to anticipate and prepare for?
That's a fair point. The challenges are significant, and they generally fall into 3 main categories: data challenges, integration challenges, and organizational challenges. The biggest hurdle, as we've kind of established already, almost always remains the necessity of getting perfectly accurate, reliable input data. This often requires a significant upfront investment in what you might call data hygiene, cleaning up, structuring, validating potentially messy, disparate data from legacy systems before it can even be fed into the simulation model. If your cycle times are estimated incorrectly by even 5%, the entire simulation result could be misleading, leading you to optimize for the wrong thing. Secondly, there's the technical integration challenge. These sophisticated simulation platforms need to communicate effectively, often bidirectionally, with a company's existing engineering systems. That means interfacing with their CAD files, their BIM, building information modeling software if they use it, and maybe even their existing operational systems like MES, manufacturing execution systems, or ERP, enterprise resource planning. Ensuring all these different systems can talk to each other smoothly, especially when they might span different software generations or vendors, is often complex and requires specialized IT and OT, operational technology, integration expertise.
Okay, data and systems integration. What about the people side of it? It's one thing to build this amazing technological system. It's quite another to get the people across the organization to actually use it effectively and, maybe more importantly, trust the results it produces.
You've hit on the third and often the most critical challenge: organizational commitment and change management. Yes, training teams and how to use these sophisticated simulation tools effectively takes time and investment. That's true. But perhaps more importantly, successful facility planning using simulation can't just be confined to the engineering department working in a silo. It absolutely requires active buy-in, collaboration, and crucially, data sharing from multiple departments: logistics, finance, safety, production management, quality. Everyone needs to be involved. Without breaking down those traditional internal data silos and fostering a collaborative approach, the simulation will inevitably lack the holistic perspective needed to be truly effective and optimize the entire system. Overcoming that organizational inertia, changing workflows, and building trust in data-driven decisions is often the hardest part of the entire implementation process.
So assuming a company manages to navigate those challenges successfully, they invest the time in getting the data right, they tackle the integration issues, they achieve that organizational buy-in. What is the enduring operational impact? If they implement a facility that's truly been designed based on data and simulation, what are the long-term rewards that justify that significant upfront commitment?
The rewards really can reshape the company's entire competitive structure, fundamentally changing how they operate. The most immediate benefit you typically see is a dramatically smoother launch of the new facility or line. A data-designed facility generally runs smoothly, efficiently, and safely right from day one. This minimizes those costly startup delays, avoids the need for immediate, expensive retrofits, and reduces operational friction significantly in the early months.
Fewer errors baked into the design means less unexpected downtime, fewer collisions or safety incidents, less wasted inventory piling up in the wrong places.
Absolutely. And this naturally leads to dramatically better resource utilization across the board. You see optimization in the use of physical space, often requiring less space than initially planned. You see better deployment and productivity of personnel. And critically, you see much higher utilization rates for expensive machinery and automation. Every element, people, machines, materials, is situated and scheduled where it should be, doing what it should be doing based on validated data. And crucially, the facility gains inherent scalability for the future. Because the digital twin has already stress-tested those future growth scenarios during the design phase, the company can often scale up production significantly later on without needing costly fundamental physical rebuilding or disruptive layout changes. Ultimately, adopting this kind of simulation-driven approach grants the company a significant, sustainable, long-term competitive edge. When your factory is operating at peak efficiency, when it's been designed thoughtfully, based on statistical certainty rather than just guesswork or rules of thumb, you are fundamentally more resilient to disruption, you're more agile in responding to market changes, and ultimately, you're likely to be significantly more profitable than your competitors who might still be relying on traditional trial-and-error design methods.
So wrapping this up, what does this all really mean? We started this conversation talking about that universal headache launching a brand new production line or factory only to find catastrophic flaws baked in, requiring those expensive, painful physical modifications. And I think what we've seen today is that the difference between a factory that's constantly struggling with bottlenecks and rework and one that's thriving and efficient, that difference often comes down to anticipating and solving those problems years before the foundation is even laid. And that's made possible by the precision of digital twins and advanced simulation platforms like the examples from DBR77 we discussed.
It really does raise an important, maybe even provocative question for everyone involved in industrial strategy and capital planning today. In a world where these powerful predictive analytics and virtual testing capabilities are readily available, they're fully validated, and their financial benefits are increasingly well proven, is the failure to simulate before you build now simply a failure of foresight? It's arguably no longer a technological constraint for most. It's becoming a critical strategic business decision that directly dictates future profitability and competitiveness.
We've explored the incredible precision required, the concept of an integrated ecosystem that links data collection, strategic planning like the DRD, execution through tools like the marketplace, and the core facility design itself. And we heard those clear, measurable ROI examples, companies saving millions, literally millions of Polish zloty, simply by optimizing things, by clicking and dragging assets in a 3D virtual environment before committing to steel and concrete. The technology really seems capable of eliminating so much guesswork.
It truly transforms facility design. It moves it away from being primarily an art, perhaps overly reliant on the historical precedent or the intuition of the lead engineer, and turns it into much more of a hard, predictive science, one that's optimized using real-world data, statistical methods, and advanced mathematics.
So let's leave our listeners with a final thought. Think about the most recent bottleneck or inefficiency you experienced at work. Maybe it was a delay in getting materials, maybe a chronic shortage of space in a certain area, or perhaps a key machine that's constantly waiting for components, just sitting idle. Now ask yourself, how much of that specific issue, that frustration, that cost, could potentially have been completely eliminated if your entire operational space had been rigorously modeled, simulated, and optimized in 3D years ago before it was ever built? That really is the power we're talking about when we discuss designing tomorrow's factory today.